Hi professors, we are Group 10 and we will be presenting our project on canteen crowd estimation. Throughout our presentation, we will provide an overview of our project, delve into the hardware and software components employed, and detail their setup procedures. Additionally, we will elucidate how these components synergize to function as a cohesive system. Finally, we will cap off our presentation with a brief demonstration to showcase our project in action. Our project is about a venue occupancy estimation system for canteens. Our setup harnesses the power of the Raspberry Pi 400 paired with the high-definition Logitech C310 webcam. To fuel our predictive capabilities, we have integrated machine learning libraries such as scikit-learn for training our regression model. Furthermore, we have implemented YOLO, an object detection framework, to enhance our system's accuracy and robustness. Our project's primary objective is to create a robust and all-encompassing crowd occupancy estimation model. This model relies on a combination of machine learning and object detection algorithms to forecast crowd occupancy based on three key factors: webcam images, Wi-Fi signal features, and BLE signal features. Crucially, our system runs inference on the edge, ensuring lightweight and efficient processing with minimal latency. This capability empowers students to make informed decisions and plan their visits accordingly, while also enabling canteen and store operators to optimize resource allocation and manpower usage more effectively.
Now, moving on to hardware and software components. In terms of hardware, we used two main devices for this project. Firstly, we have the Logitech webcam, which serves the purpose for collecting image data. Next, we have the Raspberry Pi 400, which performs Wi-Fi and Bluetooth signal capturing, as well as data preprocessing. Moving on to software, for data collection, we utilize Python's OpenCV for image capturing, alongside Linux command line utilities, Network Manager, and Bluetooth CTL for Wi-Fi and Bluetooth data capturing, respectively. For our communication protocol, we use the MQTT to facilitate transmission and receiving of data between devices. Lastly, we used Fast API to serve as a point for our Node.js app to retrieve crowd occupancy data on client devices. Now, moving on to the setup of our edge devices. The image shown depicts the physical setup of one of our edge devices. As you can see, physically, not much setup is required, as it only requires the webcam to be connected to the Raspberry Pi 400 via USB. However, in terms of software configuration, a Python virtual environment first needs to be created, with the dependencies mentioned in the previous slide installed on it. Next, the relevant Python programs need to be prepared and uploaded onto the Raspberry Pi 400. This can be achieved simply by cloning the GitHub repository on which the programs are stored. From here, it is just a simple matter of running a single Python program which serves the dual role of data collection and communication. The program internally performs an initial setup of the device as an MQTT publisher, before establishing a connection to the MQTT broker on the main fog compute device that is run separately. The program then periodically collects data using the data collection methods mentioned previously and transmits them as a JSON payload via MQTT.
In our project, we utilize webcams to capture images periodically, leveraging the Python OpenCV library for image processing on edge devices. Simultaneously, we retrieve Wi-Fi and Bluetooth signal strength data using Linux Network Manager, which is critical for understanding device count, proximity, and connectivity within the canteen. To prepare this diverse data for the model inference, edge devices perform pre-processing tasks locally, ensuring that the data is formatted properly for inference. Edge devices in the architecture functions as MQTT publishers, transmitting processed data in the forms of JSON payloads. Meanwhile, the fog computes hosts an MQTT broker and subscribes to the various topics that the edge devices are publishing on, facilitating the reception and aggregation of the data streams from multiple edge devices. This MQTT communication protocol enables efficient data flow and aggregation, which is essential for the centralization information before model inference. To perform inference, data from edge devices are aggregated based on unique device IDs, consolidating information for prediction. The chosen machine learning model is a Gaussian process regressor, featuring a kernel composed of three components. Firstly, a dot product kernel to effectively capture linear relationships and interactions between the different features. Secondly, a radial basis function kernel to smoothen data patterns and capture underlying patterns and trends in a feature space. Lastly, a white kernel component to represent and account for noise inherent. The development of RESTful APIs was done using FastAPI in Python to facilitate seamless communication and data exchange. The fork compute submits a post request to the API, providing crowd occupancy. Client devices interact via HTTP or HTTPS to send GET requests to the API, enabling quick access to the latest data of the crowd.
Here we have an example of running the data collection script. While not very verbose, it captures an image after 5 seconds so that the data collector may prepare the webcam and collects Wi-Fi and Bluetooth low energy data. The Wi-Fi collection command in standard out is shown here, and the Bluetooth low energy collection command in standard out is shown here. For deployment, multiple edge devices and a fork device will be used. In this scenario, a single edge device, a Raspberry Pi in the top left, acts as an MQTT publisher, sending the top-end wireless network signal strengths, number of detected BLE devices, and the number of people detected in an image. The edge device sends this data to the fork, acting as an MQTT subscriber, shown here as running on a local machine in the top right. The fork compute unit will then provide inference on the aggregated data from the edge devices and uses the request library to send the inference to application servers. In this scenario, the application server also runs on the local machine, providing a REST API for the fork to update the crowd status via a post request, and for end users to retrieve their published data via a GET request. This can be easily integrated into a web or mobile application should it be desired. In conclusion, this enables canteen and store operators utilize resources and manpower more efficiently through predictive analytics. Diners will also have access to information about the canteen's occupancy beforehand, facilitating better crowd dispersion. Our solution also provides a more optimized and enjoyable dining environment for both operators and customers. With high scalability, we may use this for any locations which attract crowds such as gyms or even concert venues, which are greatly scaled up versions of this project. There's evidence to suggest that our approach is applicable to other venues as well, as models trained on the Fugol dataset perform reasonably well when validated on the Kofu dataset.